Today, we want to continue solving trigonometric equations. If you recall, last time we talked about solving equations by performing inverse operations in reverse order. So one of the things that I try to emphasize is being able to read an expression. That's why we spent a lot of time when we were graphing talking about operations that happen before the trig function and operations that happen after the trig function. So I want to continue that kind of thinking when we start looking at solving trigonometric equations. So my favorite example is to look at an equation involving the expression, say, 2x cubed minus 5 is equal to 12. Something without a 2 in it. Say 14. So you have this expression, 2x cubed minus 5 equals 14. We want to look at the things that happened to the x to turn an x into a 14. And then to solve, we'll just undo those things by performing inverse operations in reverse order. So what happened was this expression takes an x and turns it into a 14. And we read the expression by saying the first thing that happens to the x is we raise it to the third power. Then we take the result and we multiply it by 2. And third, we subtract 5 from the results. This will tell us what we need to do to solve the equation by performing inverse operations in reverse order. So to turn a 14 back into x, we just have to undo all these things that happened. So first, the inverse of subtracting 5 is to add 5. The inverse of multiplying by 2 is to divide by 2. And the inverse of raising to the third power is raising to the 1/3 power, or doing a cube root. I prefer the 1/3 power because I like to read as many things as exponents as I possibly can. So then to solve, we just need to start with the 14 and perform these operations. 14 plus 5 is a 19. And I'm going to do this on the calculator because I see that there's a cube root coming up. So 14 plus 5 is 19. And then we'll do 19 divided by 2 is 9.5. And then we'll raise to the 1/3 power because that's the inverse of a third power. So we get a 2.118. We'll round it to the nearest thousandth. And so then we go to report our answer and we just say x equals 2.118. Then we have to remember, and so variations on this, just from the category, just thinking about reading expressions, we can change the order of operations by using parentheses. Parentheses are what we use to change the order of operations. So for example, if I write an equation that says 2x minus 5 and then to the third power is equal to 14, we have a different set of, the same set of operations, but performed in a different order. So this equation, to turn an x into a 14, first what's happening is we're multiplying by 2, then we're subtracting 5, and then we're raising to the third power. So our process for solving, first we're going to undo the third power with a 1/3 power. Second, we're going to add 5. And third, we'll divide by 2. Those are the inverse operations in the reverse order. So we start with a 14, and we raise to the 1/3 power. Going to need the calculating machine right away for this. 14 to the 1/3 power is 2.410. And then we'll take the 2.410 and we'll add 5 to it. 7.410. And then we'll take the 7.410 and we'll divide by 2. 3.705. So we can report out our answer as 3.705. So I had the same set of operations, but in a different order. Now, what made this problem, these two problems, very straightforward is that each of these functions were invertible. Each of these operations were invertible operations. The inverse of subtracting 5 is adding 5. The inverse of multiplying by 2 is dividing by 2. The inverse of a third power is a 1/3 power, or a cube root. We got to watch out for functions. When we're solving equations, we can't always rely on inverse operations. Not all operations are nicely invertible. So not all operations are invertible. So here's a thing to worry about. So not all operations are invertible. For example, if I have the equation x squared equals 25, we get two solutions. We can't invert the square because there are two inputs that produce one output. This equation has two solutions. X equals 5 and x equals -5. Because 5 squared is 25 and -5 squared is 25. Now I'm starting to wonder if it's the pen and not the paper, or the not paper. Well, just gonna have to cope with it for now. So we have two real solutions, and so what happens is we can't just do an invert. We have to remember this when we're trying to solve equations, when functions are not invertible. And so that's the problem that we ran into when we were looking at the equation sine of theta is equal to 1/2. If we just do the inverse function, if we just grab our calculator and do an inverse sine of 1/2, we get pi over 6, or if we're in degrees, 30. So the sine inverse of 1/2 is going to be 30 degrees, or pi over 6 radians. But this is not the only value of that. This is not the only solution to the equation. If someone asks you what the sine inverse of 1/2 is, you say it's pi over 6, and you're done. If someone asks you to solve sine of theta is equal to 1/2, you have to ask, what values of theta do you care about? Is it just the theta between 0 and 360? Or do you want all the thetas that fit this description? So we can use the inverse, the sine inverse, to solve the equation, but we have to make sure that we get all the solutions. So we have to notice that there are two solutions, or sorry, there are two angles between 0 and 360 that satisfy this equation. So there are two solutions, or two angles between 0 and 360 that satisfy sine of theta equals 1/2. "30 degrees in the first quadrant and 30-degree reference angle in the second quadrant, because that's where sine is positive. So 30 degrees in quadrant 1 is 30 degrees. And 30 degrees in quadrant 2 is 150 degrees. Or in radians, pi over 6 and 5 pi over 6. But wait, there's more. This is where we left off yesterday. There's more than this. If we think this is just looking at the circle, the unit circle, and looking at where and we're just looking at where sine of theta is 1/2. Sine of theta is the y coordinate. So we can see here are the two angles. Here's the 30-degree angle and in the 150-degree angle, or the pi over 6 and the 5 pi over 6. But there's another way to look at the sine, which we need to consider. So the other view of sine is to stretch it out. Like we've been graphing. So if we look at the graph of sine on the real number line, where we have at the middle 0, and we'll start off at 0. We can see that we're going to have way more solutions than just 30 and 150, or pi over 6 and 5 pi over 6. If we draw in y equals 1/2 on this graph, we can see that we're going to have an infinite number of solutions. So we see the first two that we found in between 0 and 360. Here's our 30 degrees and our 150 degrees in the first and second quadrants where sine is positive. But we're also going to see more later on, because the circle, we just keep going around the circle and it just repeats. So over here, we'll have 30 degrees plus another 360 degrees as we've gone all the way around a circle. And here's the 150, where we add a 360, and we'll be at 400 and 110. So 510. Furthermore, we're going to have another one, another pair, 30 at another 360 degrees after the 390. So we'll have a solution at 30 degrees and every full circle after that. So theta is equal to 30 plus some multiple of a full circle, where n is an integer. The 30 we get from the sine inverse, but we also get 150 because that's where sine is positive in the second quadrant. And then because the circle just keeps going around, we can add another full circle. So the sine inverse is, we only set up a sine inverse where the sine is actually invertible, where we'll get one input and one output, where the function is 1 to 1. We have to use quadrant information to get another solution between 0 and 360 or 0 and 2 pi. And then we have to remember that we can add a full circle afterwards. Any questions? All right, so the sine inverse gets us one solution, but then we have to remember about the other solution. So if we have a negative, that's a good question. If we have an equation involving a negative, so let's say sine of theta is equal to negative 1/2. Here's a different equation. Now, if we try to sine inverse of negative 1/2, we'll get a different value. We won't get 30 because sine of 30 is positive 1/2. But if we do sine inverse of negative 1/2, we'll get negative 30. Negative 30 is in the fourth quadrant. What we're looking for, if sine of theta is negative 1/2, the sine and the 1/2 tell us that we're dealing with a 30-degree reference angle. The negative indicates that we're dealing in, and sine being negative means we're in the third quadrant and the fourth quadrant. So we need a 30-degree reference angle in quadrant 3 and quadrant 4. So now 30 degrees in quadrant 3 will be 210. And 30 degrees in quadrant 4 will be 330, or negative 30 degrees. But we have to remember that we can add full circles. So here's going to be our negative 1/2 at 210 and 330. But we can always add full circles. So we can just say plus 360 times n, where n is any integer. And we should recognize these in radians as well. So 210 is 7 pi over 6, and 330 is 11 pi over 6. In that case, we would be adding 2 pi times n. So we should also be able to say 7 pi over 6 plus, now since we're in radians, a full circle is 2 pi, and 11 pi over 6, because that's the 330. So there will be all of our solutions in radians. So when we're trying to solve trigonometric equations, we can still do things like do inverse operations in reverse order. But we have, just like when we're solving quadratic equations, where we know that an x squared could have 0 or 2 real solutions, we have to think about all the solutions when we're looking at trigonometric equations. So that means if we're trying to solve, we should clarify, are we talking about between 0 and 360 or 0 and 2 pi, or are we talking about all real numbers? All right, I'm going to release some new homeworks today, and there will be another quiz. That's going to be it for today. I will see you all on Monday. Have a great weekend, and thanks for playing.